Hello class, and welcome to today's algebra lesson, which is about linearity and continuity of graphs. By the end of today's lesson, you will be able to determine if a graph is continuous, discrete, or neither, and you will also be able to determine if functions are linear or nonlinear. So first, we're going to understand what those words are. A reminder that functions are a relation where each input has one output. So every x that we put in is going to have a y value answer. If a function is discrete, it means every time we put in an x, it is not directly connected to that next x value. It is not, the key with discrete functions is there are no fractions or no decimals of x values. They have to be whole numbers. So for example, if you are talking about a car and the price of the car, you can buy one car and that is entirely separate from the next car that you would have the option to purchase. So those 2 points, it's not continuous between them. The continuous function, on the other hand, is something that could be connected. That is where fractions and decimals are okay. So think about that as anything that can have a half or a part. So if you are thinking about time, you could have a half an hour, or you could have a third of an hour, or you could have 2 2/3 of an hour. So there you can go in between each of those actual whole number x values. Then we have the other 2 pieces, which is linear versus nonlinear. A linear function is a function where all of the variables have an exponent of 1. We talked about that a little bit in our last lesson. But when you are looking at a linear function, it is going to form a line on the graph. So a straight line, whether it is a diagonal or a vertical or a horizontal line, it is going to be a straight line on the graph. A nonlinear function means that at least one of the variables have an exponent that is not 1. And this is going to give you some kind of curve on the graph. There's going to be a bend somewhere within that line. It could be a very sharp bend and come to more of a right angle, or it might be more of a smooth, actual curve-like bend. So we're going to start by looking once again at this summary of discrete, continuous, and neither. So the discrete values, again, not connected. There is no line between them. Each point is isolated from the other one. The domain, again, being individual values. No fractions, no decimals allowed. The range also being individual values, so not being able to go in between those points. Continuous, again, having that curve, that smooth curve, means that our x values, our inputs, are any real numbers. So I can go as far down as negative infinity and as far up as negative infinity. The range is going to be a group of real numbers. So in this case, our graph doesn't actually drop below -5, so everything above -5 would be a possible option for that range. Sometimes graphs are neither continuous nor discrete. So we have 2 dots here, which would make it discrete, but we also have the lines pointing, which would make it continuous. The inputs and outputs of those kind of functions vary based on what kind of graph it actually is. So we're going to start by identifying the type of functions. Determine if the graph is continuous, discrete, or neither. So in this case, as I look at the graph, it is connected with a smooth curve. So this is going to be a continuous graph. And the reason being is that because it is connected, the points are connected with a line. Go ahead and determine this one on your own. So this one is neither. If you look down at the very beginning of this graph, we have a small continuous piece. There is a small part that has a continuous line, and then the rest of the values are discrete, so it is overall neither discrete or continuous. Sometimes we don't have a graph of the function to look at. We are just given a table. So we're going to use the table to determine if it is discrete or continuous. So looking at the information I'm given, my inputs are books. So I have 1, 2, 3, 4, and 5. We know that we can't be selling a half of a book. So this is going to be discrete. And the reason being is because the inputs, so the domain, is made up of individual values. So it's made up of values that cannot have fractions. Go ahead and try this one on your own. In this case, we have a continuous function. If we look at our inputs, our hours, you can have fractions or parts of an hour, so it would be connected by one continuous line. Now we're going to determine whether functions are linear or nonlinear. This goes back to looking at the exponents. So I've got C plus D is equal to 19A minus 4R. If I look at the exponents on all of these, each of them have an exponent of 1. There's only one value. So this would be a linear function because all exponents are equal to 1. So we have all of our exponents are 1. When I look down at this second function, this is one of the ones that is a little bit trickier. It looks like all of our exponents are 1. However, because there is an exponent in the denominator, what that actually means is your exponent is a negative. So this function is really saying 2x to the negative 1 is equal to 72 minus 9y to the 1 plus 8b to the 1. So this is not a function because there is an exponent of negative 1. So if you have an exponent in a denominator of a fraction on a variable, it is no longer a linear function. Go ahead and try to determine if these two are linear or nonlinear on your own. In this case, the first one is nonlinear because there is an exponent other than 1. That first x has an exponent of 3. And in the second one, it is a linear function because all exponents do equal 1 because our variable is in the numerator of our fraction. Finally, we're going to determine linear or nonlinear based on a table. In order to do that, you are looking at the change values for the y's compared to the x's. So in my first group, I go from 0 to negative 1, which is a change of negative 1, compared to 0 to 1, which is a change of 1. Then in my next group, I go from negative 1 to negative 8, which is a change of negative 7, and then from 1 to 2, which is a change of 1. Then I have a change of negative 8 to negative 27, which is negative 19. 2 to 3 is 1. Then I'm looking at negative 27 to negative 125, which is a change of negative 98. and that one is over 2 because I went from 3 to 5. And then our last one, we've got negative 125 to 343, which is a change of negative 218. And again, our change is 2. So looking at all of these different change values, if it is linear, these values will be the same. If it is non-linear, then our values will be different. So in this case, it is going to be non-linear because the rate of change is not consistent. So we have different values for each group of change. It is not consistent. So you have to have those rates to prove that that second statement. Go ahead and try this one on your own. So we've got 4 over 12, 3 over 1, 6 over 2, 3 over 1, and 4 over 12. All of those fractions would reduce to 3, giving us a consistent amount of change, so it is a linear function. If you have questions about this or anything else from the lesson, please feel free to reach out and let me know.